doing a lot of jobs, very well paid.
Yeah.
As long as it doesn't continue, definitely.
I talked here before.
Sorry.
No, it's not. But I must have. This room looks very good.
Perhaps if
Why would Cronin have sent me a wouldn't be in his hand?
well, you know, there was a faculty member here for 6 months. This was during the he wanted their resident to we were just building it. We didn't want to do that.
Oh, right.
Called the chair and says, you know, we have to go to Laurie here. And he wants to become a faculty member. What do you say to that? So, of course, he became a faculty member. And the whole point was that he was going to influence us by cranking up the administration's pressure on him. And it didn't work. We didn't get influenced. So they left. But he is our one and only Nobel laureate in the house. He's an interesting guy.
Yeah, I really loved working for him. He was a great guy. He would have never have left me because of half an hour. And when I was in the job market, it was friction. I had to go. That sometimes would clash with his agenda on who's we talk to. It really caused trouble for about a year until I understood. Once I deal with it. It took a year. You know, I went through a full cycle of the job search before I understood what was happening and how to deal with it. Once I did it, I wish someone had sat me down and just said, this is the way it is. Would have saved me a lot of time.
Being on his bad side is not a good idea.
I was never on his bad side. He considered talks was something that he pulled out and wasn't something that he oh goodness. Goodness gracious.
What about that? Can you check it out?
Okay. Straightforward. We're not getting too. So it's not like a it's not Japanese regional airline.
Either Anna or Jao. There's no Delta partners. Japan anyway, jets are huge, especially peach aviation. This is like running a horror story. How they shovel people into hangars, boondocks. Jetstar, actually Jetstar sometimes punches with a Jao. That's pretty great flying, not the wrong flights. I know. That's what you pay for. I mean, we'll be okay.
That's what I think.
It's a complex.
Sephora has heard one of the sick
The resort does nothing.
Because we have category theory, and also we have that was a trivial exam.
But I think it's very
Martin supplements.
I'm trying to figure out how old this man is.
no idea. One feature of the front of your university doesn't mean
The library is good. Oh yeah, it's not the but that's the library. Where's the building?
It's just off the edge. Our committee.
Folks. Hello.
Do me a favor. All people have to.
All right, it's a pleasure to welcome today's speaker to our colloquium. Some of us have known Leslie for quite a long time, but very episodically. So my, I think most recent clear memory was Moscow in 1987, where we were desperately looking for a restaurant with food in it. And somebody pointed out that all the restaurants are called pectopause, because if you read the Cyrillic in English, it's what it says. Restaurant is pectopause. So things have changed markedly in Moscow in over that period of time, and as has Leslie's research direction. So he was originally in cosmic rays and actually worked with us back in the good old days at Dugway Proving Grounds, and he's now, of course, one of the leading experts in Axion searches. So Leslie got his undergraduate degree at UCLA, did some work at the Bevel-Ac, and he did his graduate work at the Stanford Linear Accelerator, where he worked on E+ E- collisions. Then he went to the University of Chicago, where he got involved in cosmic ray physics with Jim Cronin, some of you remember. Then at some point, his interest veered from cosmic rays to dark matter, and whereupon he went to Lawrence Livermore, University of Washington for a while, and finally settled down. They skipped the MIT. Anyway, that's spotty history. And eventually wound up at the University of Washington, where he is currently professor of physics. So he will tell us about dark matter axions.
Thank you. Thank you for inviting me. It's been a while. Talk outline. You're probably not all that familiar with the QCD dark matter axion, so step one is I'll do my best to explain it in the time that I have, and given my understanding. There are bounds on the properties of this thing, its mass and coupling so far, and I'll talk a little bit about that. There are three flagship surges that involve RF cavity experiments, solar, axions, laser, almost focused completely on ADMX, which is the project I'm working on, which is RF cavity. If time permits, I'll talk about these two other flagship searches, which are very interesting, and then I'll reach some conclusions. sensible conclusion. To start, dark matter, there's two things going on. There's dark matter and there's QCD. We'll start with dark matter. It's a long-standing problem, as you well know. In the 1920s, there was this famous paper, I guess at the time it would be most cited, and you called it in that epoch, and the idea was we're realizing we're in a galaxy. What are the properties of our galaxy? What's the potential nearest, etc. So Kapteyn did studies of motions of type G stars and came to this odd result. This is in the 1920s, that he couldn't quite reconcile the motions of the stars with the masses that he thought were there. And it was a fairly glaring discrepancy that was ignored. And then in 1920s, people know that Oort reached a similar conclusion. That was early 1930s. And then Zwicky and Smith separately, their groups, looked at, for instance, the Coma cluster, et cetera, and they found that these things had virial velocities that were enormously big. This cluster of galaxies, it should have blown up ages ago. The inference is there's a lot more mass than there ought to be. So this is a long-standing problem. It started in the 20s, where as far as I can tell, the first invocation of the words dark matter problem first appeared, and went to the current age. So the current age, this is some of the evidence. The evidence is really overwhelming. It's just across all fronts for dark matter. But this is some of the evidence. Rotation curves of, what planet is here? Rotation curves of spiral galaxies. This is distance of hydrogen, essentially, from the center of a galaxy. And this is velocity on this axis. If all there was the visible matter, you would see this. But in fact, what you see is this. And so in every spiral galaxy you look at, there is a non-Keplerian behavior of this so-called rotation curves. Some look better than others, but none of them behave in a properly Keplerian way. This is a really direct way to look at dark matter. You look at a rich cluster of galaxies, and you see these arcs. That arc comes from bending of light as from matter. So, and what you find is that these background objects that are bent, you can invert this and find that there's a lot more mass in this than there ought to be. And further, it's not even point distributed where the galaxies are. It is broadly distributed across this cluster. So it's more evidence. This is yet the final piece of evidence. These are acoustic oscillations in the microwave background. They tell us, just like if you were to bounce a spring, the mass comes into the oscillation frequency. The mass comes into this oscillation frequency. In this case, it's multiple moment. This is the correlation function. These acoustic oscillations depend on the mass density, and the inferences on very, very, very big scales, gigaparsec scales, there's lots of mass. So we'll take that as an axiom. There's now a good question, which is, what is this stuff? If it were hydrogen, neutral hydrogen, you didn't see it, it wouldn't be so interesting. If it were bowling balls, it wouldn't be so interesting. If it were black holes, maybe that's a little more interesting. It's not atoms, it's not low-mass stars, not black holes, not neutrinos, probably not black holes. In fact, it's not anything in the standard model. Nothing in the standard model really fits what this stuff is. There are two known unknowns. You've probably heard about WIMPs, weakly interacting massive particles, and axions are the other known unknown. And this stuff, this dark matter, this is the cosmic pie here. This is the mass and energy density on the biggest scales, and about a quarter of the mass energy density that clumps gravitationally is some unknown stuff. WIMPs, axions, or some unknown. And most of the rest is stuff that repels, not clumps, called dark energy. It's really quite a mystery. The QCD axion. So we'll leave dark matter. We'll go to QCD. So QCD was conceptualized, let's say, in the 1970s. And it wasn't so different in terms of its discrete symmetries like parity, charge conjugation, etc., than quantum electrodynamics. Namely, it's supposed to be symmetric. And later in the 70s, people realized that's not true. QCD is radically different when it comes to its symmetry properties than electromagnetism. In particular, QCD, quantum chromodynamics, the theory of the strong interactions, expected to violate CP, not conserve it. So CP is the product operation of changing charges to anti-charges, so plus charges to minus charges, and looking at the system in a mirror, sort of looking in a mirror. If everything behaves the same way, that's a good symmetry. QCD is expected not to be a good symmetry, and if you doubt it, you can take the vacuum of QCD, run it on a lattice, and you see these blobs in a certain kind of space-time. They're called instantons. You've probably heard about them. This is the vacuum of QCD. It's radically different than the vacuum of quantum electrodynamics. If you took my graduate electrodynamics course this quarter, and I ask you what the classical vacuum of quantum electrodynamics is, it's trivial. E equal B equals 0. Couldn't be easier than that. For quantum chromodynamics, this is one of the infinite number of vacua where the color E and the color B are certainly not 0. These are CP violating. They're called instantons because they appear and then they disappear. They're there in an instant and they carry quantum numbers of CP. When they disappear and when they appear, you're changing CP of the system. QCD is radically CP violating, one expects. However, the neutron has an electric dipole moment that isn't observable. It's expected, because of these processes, to have a dipole moment of something like 10 to the minus 16 e centimeters. That's huge. The current bounds are order 10 to the minus 26 e centimeters. There's a 10 order of magnitude discrepancy in a prediction of the standard model. 10 orders of magnitude discrepancy. It's the biggest discrepancy I know of in the standard model. It makes all these 3 sigma effects look paltry. It's called the strong CP problem. And here's what Peche and Quinn did in the 1970s. At the time, they did what was very trendy. They introduced a new axial symmetry into QCD. It's hidden. It was broken, spontaneously broken. In fact, it's broken if you think about it, but I won't go into details. And like all Higgs processes, when you have a spontaneously broken symmetry, you get a Higgs-like particle, you get other couplings. Those other couplings cancel the CP violation, and the new axion-like particle, the new Higgs-like particle is called the axion. One of the names, in fact, for the axion was Higgs, because it's Higgs physics, even simpler than Higgs physics. Axion 1. It shares the axion quantum numbers are basically those of the pi naught. They're both pseudoscalars. They have a different mass, and you can relate, therefore they can mix with each other. You can relate the axion mass to the mass of the pion, sort of around 100 MeV. We know the decay constant of the pion. We ask our high energy people. We make a guess on the decay constant of the axion, and that gives us the mass of the axion. They're intimately related. So that's all of that, almost all of axion physics. So axions and dark matter, we'll put the two pieces together now. Okay. So the idea is as follows. The universe, early universe, there was a big bang, the universe was hot, it was above some symmetry breaking scale. The universe eventually cooled, this new symmetry is broken at some scale, F sub axion, and axions appear. Okay? However, there's some angle associated with this new symmetry. It's very unlikely, a priori, that angle had anything to do with the cold angle. And so that angle oscillates about the minimum, the one we have now. Those field oscillations, that oscillation of that angle is dark matter, is the axion. And boy, this came out funny. The density of axions relative to the critical density is related to this misalignment, this theta angle we call it, and the F sub A. This is this decay constant. So now all the pieces are there. If you want axions to be the dark matter, if you want axion density to be about the density, the critical density, and you want the decay constant to be around 10 to the 12 GeV, you get mass of the axion of a few micro eV for theta of order 1. That's what you kind of expect. It's very hard. So you can make this into a better mass estimate by far, but it's very hard to evade this because the axion and the pi naught mix. So you can't deviate from this too far without wiggling your ears. Then one final slide is this is Wilczek on the right and a cleaning detergent called Axions. Wilczek claims in his Nobel lecture he named them after laundry detergent. Who knows? Because it cleans up the problem with the axial current. Okay, great. Last theory slide. This was given to me by Ann Nelson when I had to defend axions to the Department of Energy. They're very simple people. They have 10 neurons. And I couldn't have given them the arguments I just gave them. This is the argument I gave to the DOE. There are viable theories, and you could look at some viable theories. There are natural and elegant theories. These are some of them. Theories with dark matter axions are the intersection of viable theories and natural and elegant theories. Great. So you can ask the question, what's the axion mass? We just answered that because the axion and the pi naught mix. We know the mass. It's going to be light. It's probably lighter than the neutrinos. Micro eV, 10 micro eV, 20 micro eV, something in there. What about its coupling to normal matter and radiation? Well, that's really in general hard to predict. Really in general hard to predict. There's a new U1 symmetry hanging around. That's what started this game. Hence, there are unknown U1 couplings. We don't know what they are. However, this is a golden process. Axion goes through a loop, turns into 2 photons. This is just what the pi naught does. And it contains loops with color. It contains loops with quarks. It contains loops with leptons that don't contain color. And they appear in the ratio. There are 2 benchmark models that people talk about. One benchmark model is called KSEZ, named for the originators. It's called the hadronic axion. This is where there are no lepton couplings. The electromagnetic part of that vanishes. Only colored couplings. The more compelling, at least to me, is the so-called DFSZ. This ratio becomes 3/8. 3/8, as people know in guts, is a magic number. It's the unrenormalized sine squared theta W. And the assumptions that go, this is ad hoc, the assumptions that go in here are only that there's unification and you get sine squared theta W unrenormalized of 3/8. That's pretty simple. So the DFSZ is so compelling that it was recognized a very large number of years ago that in order to have a really sensitive search that really said something about whether you find axions or not, you need sensitivity to this DFSZ axion. The problem is that these are some of the weakest couplings around. They're a factor of 10 weaker than this. So that was the challenge. But we recognized this many years ago.
As far as coupling to electromagnetism is concerned, is it coupled to E dot B now? Since it's a pseudoscalar?
Is it what?
Is it coupled to E dot B? Since it's a pseudoscalar? I couldn't really follow.
Yes, but it requires a little statement. There's not a tree-level coupling of E dot B. This isn't the tree-level coupling of axion to 2 photons. This is a coupling of axion to quark, axion to lepton, and axion to something. There is no tree-level coupling of axion to 2 photons. E dot B, one of these would be B, one of these would be E. There is no tree-level coupling. However, there's an effective coupling for this process, which is axion E dot B. Okay? There's an effective process because there's a loop when you look at it microscopically.
So I can tell that you're drawing that, but why is there no direct coupling? E dot B is a pseudoscalar, you have a pseudoscalar field.
I mean, I guess you would cobble something up. It has no color charge. It has no electromagnetic charge. Why would it couple to a photon?
Sorry, I don't know.
You would have maybe if you endowed an axion with a tiny electromagnetic coupling, maybe. But it's not natural. It's not the way you invented the axion. You invented the axion to solve the strong CP problem. it must have coupling to color to do that. Whether or not it couples to electromagnetism is optional. And if you want this guts thing to work out, which is another way of saying you want anomaly cancellation, you have to have some coupling to leptons. There's nothing in there that requires at all that you have a direct coupling to photon. Although some clever person could probably do it. Yeah?
In the previous slide, you talk about FA in the scale of GeV. One slide before, somewhere. Yeah. So then, in the two-photon decay model, is FA is equal to the sum of the two energies of two photons?
No. Nothing to do with it. It's the symmetry breaking scale.
And so why it has to be in the 10 to the power of GeV? Why you pick that value?
This doesn't have, the two-photon coupling doesn't have anything to do with this. This is the amount of, after you have this phase transition where axions appear, you can ask the question, what's the density of axions in that, right after that phase transition relative to critical density? Okay? Obviously, it has to be proportional to theta. If there's no misalignment, you wouldn't produce any axions. If theta's bigger, you produce more axions. FA appears in this, yeah, it's kind of tricky, but FA appears in this the same way when you have a pendulum. So imagine you had a pendulum and it was in free space, you were in orbit somewhere. It's just at some angle, theta, some initial angle theta. If you turn on gravity very, 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 very slowly, okay, the pendulum slowly goes down and stops. If you turn it on rapidly, the pendulum oscillates and there are energy stored in the oscillation. There are two constants in that pendulum problem. There's the length of the pendulum and there is a mass floating around. Well, actually, there's the length of the pendulum. I didn't want to say mass. The length of the pendulum, and there's the speed that you turn on gravity. Okay? There's a dictionary that takes you from that to this. This is exactly the same problem. The length of the pendulum is 1 over the mass, and the speed of that you turn on gravity is lambda QCD. Okay? And the factor of 1.18 appears because you're in expanding space-time, and that pendulum argument would be perfect, except you get an extra dissipative term because you're in expanding space-time. So it's exactly a pendulum with one extra term, but the physics is identical. It doesn't have anything to do with couplings to photons. Once you make those axions, they're dead inert. The couplings are so tiny, they're never in any kind of thermal equilibrium. Nothing happens to them. But we haven't shown that yet.
Can I ask you something? Sorry.
Yeah.
So if I look at that coupling, E dot B times something, and I vary it with respect to electromagnetic vector potential, I will get a current. So what is that current?
So that is, if you were to take a loop, this is a really interesting question because you're asking about Maxwell axion equations. If you were to do an experiment of take a big magnetic field and drive it through in some vertical direction, and if there were ambient axions around, that loop would appear to have a magnetic flux, which has a dot in it. It would be the time derivative of axion in it. So that current turns out to be the effective EMF effectively around this loop. So there is a current associated with it. Okay? So if you Google axion Maxwell equations, there are new currents that appear that go into a Faraday-type current. They actually can induce an EMF around a loop, even though it's not really a time-changing magnetic field. So yeah, there are several currents floating. So, what's the axion mass? This is a great question. We did an approximation. We said axion mixes with pi naught. Yikes. Actually, I got to speed up. This is all great questions. Axions mixed with pi naught And to get the mass of 1, 10, 20, 30 micro eV for the axion, that's actually pretty robust. Here is a compilation of modern estimates of the axion mass. This is 1 micro eV, 10, 100. This is now a great plot. This is this effective coupling of axion to 2 photon. These are these 2 model lines. KSVZ is here, DFSZ is here. And there's no particular agreement. These are old experiments. This is our old experiment. These are older old experiments. And this is where our current experiment is going up to. So I don't have great precision to tell you about the axion mass, except there's an industry of computing it. Theoretical restlessness. Theorists are very creative people. They're restless. They don't, they're hard to corral. So could axions couple more strongly? It's not easy. So you have to ask the question, which do you want to throw out if you want to do that? The unrenormalized sine squared theta w or the unification? If you want to throw one or the other out, fine. Could axions be much heavier? Could they be above 10 millielectron volts? Not easy. They're now bounds from supernova, bounds from white dwarf cooling. Axions are cool white dwarfs. There are now neutron star bounds. These are extremely interesting. They're just coming out. There are neutron stars which are hot, old neutron stars. They're blocked from cooling. If you had axions, they would cool them. And there are bounds on that. Could they be much lighter? Could they be nano EV, femto EV, 10 to the minus 20 EV? Not easy. If you make the axion lighter, so if you make Fa bigger, you overproduce axions. You have to deal with that. There is something called isocurvature fluctuations in the early universe. There are bounds on that. You have to control them somehow. You need to fine-tune the scale of inflation. As you make axions lighter, you have to move the inflation scale so you don't cross over it. And eventual problems, even if you keep doing that with baryogenesis, et cetera, et cetera. So very light axions require either fine-tuning special scales or new physics. And then, so we're to this point, a credible QCD axion detector, a dark matter detector, should search in sort of the general mass range, and I'm willing to fuzz the edges, 1 to 100 micro eV at DFSZ sensitivity. So that's, over the years, that has become more or less the target. And this was a talk given by Dine a year ago, 1917, not even a year ago. So he looked at all the parameters that one could have for axions, and we're more or less looking in the right spot in terms of the axion parameters. I'll skip this. Axion bounds. So people have tried to bound the mass of the axion experimentally. The first paper I know of is this paper, and it bounded axions and Higgs. It's probably a wrong analysis. It's fun to read about it, but it's the first effort at it, and then it's become an industry. So this is sort of the summary of the industry. This is, again, the putative mass of the axion. This is this coupling into 2 photons, the KSVZ, DFSZ, the allowed mass is here. And there are all these experiments. These are all methods of looking for the axion, and there's only one that cuts into the model space where you really want to find them. You want to be here. And that's the so-called microwave cavity method. So that's what we're going to focus on. Sorry. So the idea of this is as follows. On the upper left is a microwave cavity. It's threaded by a magnetic field. So you don't see the X's here. This is a solenoid magnet with a vertical field. This is a microwave cavity. A nearby axion scatters off a virtual photon, a zero energy photon in the field, and now it pops a real photon. If the axion is in the micro to 10 micro to 20 plus-ish, it's a microwave photon. 1 gigahertz is 4 microelectron volts. This is a microwave photon. And what you expect to see is a little burp in the power spectrum within the cavity corresponding to the axion mass. And the width ought to be more or less the virial width of the axion. It's a very interesting question what the virial width is and all this stuff, which I'm finessing. Another thing I wanted to mention is that this is the speed that you can search for axions. By that I mean an RF cavity has a resonant frequency. You don't see all frequencies at once. You see a frequency which is sort of the Q width of the cavity. So at the Q width, you get an enhancement of axion production. Off resonance, you get off resonance production. The width that you can scan is proportional to 1 over the system noise temperature squared. This would be very familiar to radio astronomers. So if unluckily you had 10 times the noise temperature, it would take you 100 times longer to scan. So system noise is the crucial parameter in this search. This is our experiment. It's called the Axion Dark Matter experiment. It's got a bunch of universities here and labs, etc. And this is the realization of that idea that was originally due to Pierre Sakivi in University of Florida. This thing is about 4 or 5 meters tall. This is the whole cryostat. Here's the magnetic coils, the RF cavity, quantum electronics in the cold space. So the system noise is crucial. The only way to get really good system noise is to transition from transistors to quantum electronics. And the rest is cryogenic support. This is us testing the magnet. And there's a couple interesting things. This is a patch, the square thing, where a persistent switch failed and blew out the stainless steel cryostat. That was interesting. The other thing is this is powered up to 8 Tesla. And you can see the leads are being yanked apart. If you look very carefully, you can see dipole field lines with wrenches here. And I'm standing in a high field, so I shouldn't show this to the Department of Energy. Quantum amplifiers. So one of the things that happened is we actually did research with John Clark at UC Berkeley on microwave amplifiers with quantum electronics. And 2 things came out of it. SQUIDS, superconducting quantum interference devices. This is based on Josephson junctions. And Josephson parametric amplifiers. These are 2 very devices that depend on quantum tunneling, superconducting quantum tunneling, to amplify microwaves. I won't tell you how it works. These are 2 realizations of it. I'll tell you the results of it. This is a test of these devices. This is noise temperature on this axis. Sorry, I just said noise temperature. This is physical temperature on this axis. And this is the noise temperature. That's the coin of the realm in measuring noise. Quantum mechanics puts a limit on the noise here. It's from the uncertainty principle. You can't have 0 noise in an amplifier. You'll violate the uncertainty principle if there's any gain. The best transistor amplifiers are here. They're off the scale. You can see as we cool it, we start to approach the quantum limit. And this is kind of an old plot. We're now sniffing at the quantum limit. This is one of these little devices being fabricated by one of the postdocs, actually. This is kind of fun. This is the log of the number of samples that we take, the averages. And this is the fluctuation in the power over the power when we do the averaging. It falls like square root of number of averages. So we hit the 30 days of integration. That's 1 microwave photon per minute. Okay, so we're systematic limited. This is really eye-watering to 1,000th of the power of a DFSE. That's 10 to the minus 26 watts. We ran out of units. The smallest SI unit is the Yocto watt, which is 10 to the minus 24 watts. We no longer have units. I know of no other experiment which is sub-Yocto anything. And there's a story about this. One of the people in our group sent to the System International a request for a small unit. And they got a reply back with an envelope with wax and ribbons. I never heard of email. Anyway, the tuning now is, there's a small cavity here that we use for testing. I won't go into it. Tuning is now with piezoelectric motors. I'll just say that they work at deep cryogenic temperatures, high vacuum high magnetic field and give you fantastic position resolution, nanometric position resolution. I'll leave it at that. This is just a fun picture of the insert going into the bore. And you really can't see much. These are thermal shields. This is this helium reservoir. These are more thermal shields. It's going into the bore, it's coming out of the bore. It's kind of a fun photo. This is a cool down. To get quantum limited noise, you need a big dilution refrigerator. We have a huge dilution refrigerator. And this is just typical cadence of a dilution refrigerator that any condensed matter experimenter would see. We cool the experiment to liquid nitrogen. Boom, there it is at 77 K. We cool it to liquid helium, boom, 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 boom. There it goes at 4.2. We turn on 1K pots, bring it down to 1K. We turn on the Dilfridge still heater, boom, 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 and you're down to deep cryogenic temperatures. It only takes you, 4 or 5 days to do that if things work. If they don't work, it takes a month. And there's a picture of the Dilfridge, huge Dilfridge on the right. This is just our typical run cadence. This is time on this axis. This is the frequency that we're scanning, and you can see that we just click along. We integrate, integrate, integrate. You don't see the individual steps here. There are individual steps. That's a low frequency channel. We have a high frequency channel as well, I didn't talk about. We just more or less run in that mode. When things are going well, that's sort of what we see. This is what we would love to see. This is fake data. I shouldn't say fake data, but this is a frequency on this axis. This is honest-to-God data. This is kind of interesting. We have the luxury in this experiment of, at the bottom of the experiment, we insert an RF signal that mimics the axion and mimics the amount of power deposited in the cavity. So in a typical experiment, you do that in software. So if you're in a WIMP experiment or something, there's really no way to inject it when you're operating a fake WIMP. We inject a fake axion when we're running, and it does two things. It tells us that our system is running in a reasonable way. And the other, when we say we have a 90% confidence of seeing an axion across some bandwidth at some power, we literally mean that 90% of the axions that we inject, we come through our analysis chain. So our confidence level is the most primitive confidence level you can imagine. And this is not the signal strength that we expect. It's a highly inflated by hundreds probably signal that we expect. We really expect 4 or 5 to 1, and this is obviously much bigger than that. And that's sort of the shape, though, that we expect to see. It's kind of a distorted Maxwellian. That's what we expect to see. This is recent limit.
You can inject the axion, then this RF axions can just come in from outside too, right?
This RF connection.
Or so you're saying
We
you
get
can mimic these events with the RF thing.
Yeah.
So what if there's some accidental mimicking of these events?
Oh, so what happens is we didn't mention the cadence here. That becomes a candidate. There's no way for us to tell a priori whether that's a candidate axion or a injected axion. So we have to go back and rescan that. So one of the things about an axion is it's not like a WIMP search where you run for a year and you might have 3 or 5 events. And you can't answer in one day if those are background or not. For our experiment, you can. If we have a signal at a certain frequency, we can sit there for 20 minutes if we wanted to and get incredibly high signal-to-noise ratio. So when one of these candidates come in, we have to go back and sit on it and see, is it a background or is it a true axion, candidate? So yeah, it appears on our candidate screen. We don't know how to tell whether it's a candidate or not. So we have to treat it as a candidate.
So how do you scan over the frequency?
It's simple.
You change the light?
We change. This violates the rule of thumb of never go backwards. But I will do it. Whoops. That violates the rule of thumb of hit the right button. I see tuning rods here. Nope. Let me go here. This is a small version of our experiment. Tuning rod on a shaft. This thing tunes. When it's near the wall, it runs in the TM mode. There's almost no effect on the frequency. There's no field there. When you move it towards the center, that's where the big field is, you get more of a frequency show. We move the rod. We can do it exquisitely well with piezoelectrics. We sweep the cavity. We can measure the resonant frequency exquisitely well. That's straightforward. If it's not right for some reason, we iterate, but typically it's right. We integrate that signal for about a minute. We make then a small step compared to the Q width of the cavity, and the Q width is about 100,000. So the cavity width is about 10,000. So we step by 1 or 2K. We repeat. Rinse, repeat, rinse, repeat. And that's our data set.
The Q value is the same?
No. No. There can be subtleties. When you have a bare cavity, the Q is the Q. If you don't see the Q of 200,000 bare, you've made a mistake. The plating is bad. The connection is bad. Something. If you put a tuning rod in with probe, you're changing that, and there could be subtle impedance differences. They aren't radically different, like it doesn't go to 5, but you can have slow variations in Q because of the geometry. And when you're near a mode crossing, there's real subtleties coming near mode crossings, where I won't go into that. You could have two modes that are almost degenerate in frequency, and then things get wild. This is interesting. This gives you a flavor of our current bounds. This is recent bounds. This is a 90%. These are, again, these two plots. Here's axion mass. On this axis, we're few micro eV. The top axis is cavity resonant frequency. This is, again, coupling the two photons. This are these two models. We've now blown this up quite a bit. We're sitting at this kind of sensitivity down here below DFSE now. In future running, we will run here. We'll move it closer here to not, as we say, waste time running here. But that's our current plan. We set a very conservative bound on where we're going to run in case a systematic error came up and we had to then degrade our bound.
So for this lower bound, given this coupling, let's say we are sitting on the lower bound. Okay, so the axiom mass is 2.7, and the coupling is like this. So in your experiment, how many like these RF photons that got produced per day?
Handful of hertz of microwave photons. Hertz.
But
Hertz. A few per second.
a few percent.
Yeah, a few microwave photons per second. So it isn't a lot. And there's subtleties here about when you're low numbers, you have to take care, etc. But we think we've taken care. Yeah. And as I said, our sensitivity is actually better than that. That's nominal sensitivity. That power there corresponds to something like 10 to the minus 23, a little less than 10 to the minus 23 watts. We can actually go to 10 to the minus 26 watts if we had to. We could go to subhertz sensitivity if we had to. This is our running plan. In 2017, this is again the same flavor plot. Too much dark matter. You start getting into issues with astrophysics here. Supernova, white dwarf, neutron star bounds are up there. Our old data, it took us 10 years to do this blue. This is 1 year of the current experiment. So that's our plan, and it goes into about 2021 of operating this thing. And you can see our reach. We're trying to get up to a mass of 40 microelectron volts. That's our goal, and 10 gigahertz in the units that I use. What about other players? Other people do this. It's worth looking at it. This is the same plot. Us, other experiments. This is our sort of current bound here. There's an experiment in Australia, small cavity experiment. There's a Yale experiment. This is probably the one that's closest right now to at least one of the target ranges. If you want DFSZ, you need another order of magnitude. that 1 year of data for this narrow needle becomes 100 years. So there are other experiments. Right now, there aren't real competitors. In 5 years, there could be real competitors. I will move on. We have plans to go above 10 gigahertz. They're wonderful plans. Solar Axion searches, everybody loves them. I'm not going to talk about them. They're one of the flagship programs. Let me get to, I do want to say something about this. I don't want to give it too short shift. The sun might be a source of axions, and you can brem off, for instance, an axion from a nucleon in the sun, and it could come to Earth, and you could reconvert it in a magnetic field. There are big experiments to do that. CERN has the CERN Axion Solar Telescope. They're not doing much now, but they're planning on a big experiment. Oops, I passed it, called IAXO. It's not funded yet. We're still doing R&D. Huge thing. Where's the size of a little person? A little person would be here. This is a steerable, multi-bore superconducting magnet. Ain't cheap. It ain't going to be built tomorrow, but it's the next phase of this solar axion stuff. There's another experiment you can imagine a search where you generate a photon, a polarized photon, and because the axion interacts with E dot B, as he noted, one polarization has different propagation properties in a vacuum than the other polarization. Okay, because you could produce an axion, you might split off an axion and turn the rotation. So if you look for rotations, so you could have birefringence, for instance, you can look for axions in vacuum. The next generation of that adds Fabry-Perot cavities. There's locked Fabry-Perot cavities. The sensitivity, well, the power conversion is the square, finesse times finesse. And the sensitivity is the square root of that, but you can get finesses up to 1 million. So that has re-enthused people about this technique. And DESI in Germany with ELPS 2 is probably the strongest realization of that. This describes sort of the state of the art now. This is putative mass, again, the coupling of axion photons and the lines here. In the near term, we're going to get this micro EV range to a handful of micro EV. Somewhat later, we're going to get this next decade here. Okay? And then we don't have current plans. This is probably available space. Above 100 microelectron volts is to be perfectly plausible. And there's no plans of anyone now to do that now. It could be perhaps that CAST will go from this blob of sensitivity to this blob. They would argue with me probably about what I'm doing. That's crudely what you get. The early laser experiments were up there. They're improved by a big factor. They're probably going to go to here. So that's the landscape into the 2020s of axion research. You want to be sort of, for dark matter axions, you want to be in this range here. There's this technology, if you believe in variance or God being capricious, there are other ways to do it. Conclusions. What's conclusions? Conclusions 1, conclusions 2. So conclusions 2 is listen to nature. I always do. Certainly keep your eye on the LHC and WIMP detectors. They're quite powerful. They're plausible. The jury is still out on them, but if they remain undetected, you might want to look hard at axions. These are just some bounds on SUSY for whatever it's worth. There are people here who know this much better than I on SUSY at LHC. And let me get to my conclusions here. The axions are a compelling dark matter candidate. They're certainly explain the dark matter, strong CP problem, et cetera, et cetera. To me, they're more natural than other dark matter candidates, but God doesn't check with me all that often. ADMX, it's just yesterday. I haven't heard from her in ages. This is the leading experiment, this ADMX Gen 2, searching for dark matter axions. It's going to search in the sweet spot all the way up to about there. And there's some things that might happen there. Well, that's micro V. We're up to here. So it searches up to here. This is probably the most plausible range right now of axions. People's mind could change, but that's it. And this is the only experiment now, or even in the near term, sensitive to this DFSZ coupling, where you need to be to have a credible surge. And the status of the experiment, we're in production data taking, and we are, as you saw in our plot of our physics range, we're slowly moving up in this. And I want to thank our research sponsors. So thank you very much.
Questions?
So I work on the New mission, and I remember one of the things, one of the objectives was looking directly at the sun and looking for axions, in the core, interacting magnetic field. So where would limits from that fall on?
It depends how blunt you want me to be.
Very blunt, please.
There was an early bound which made no physical sense. That people said they had spotted axion emission from the sun. It made no sense. That kind of faded. If you're looking for axions from new star, they would be perversely, you'd have to produce them thermally. Thermally produced axions aren't very abundant. The couplings are just exquisitely weak. They're incredibly rare. The acceptance area of something like new star is incredibly small if you try to convert it. There are ideas around, so here's a typical idea of new star. Axions are produced in the sun. Has to get through the magnetic field. It gets converted into X-rays because we have a lot of kinetic energy, KVs of kinetic energy. Those X-rays might hit new star and you detect it. When you go through the numbers, it would be in this range here. There are people who argue that there are ways to evade that grim outcome, but it requires an unusual, to my mind, set of assumptions. So I suspect, to be blunt, that new star isn't going to contribute much to the QCD dark matter axion. It might contribute to these alternatives that they call ELPs, any light particle, which have different properties than the QCD axion. So it may be a different class of particle. It's much less constrained, though. That's the problem. As soon as you jump into that, everything is wide open. It's the Wild West.
And in the other experiment you were showing, you were using new star-like mirrors as part of that.
Well, it wasn't new star-like mirrors. That was a different thing. That was to build up coherence in this. So these two Fabry-Perot cavities were locked. And essentially it's ADMX. So ADMX has its high Q cavity. And if you have a process where you make the density of final states huge, the rate for that process goes up. When you may have a high Q cavity, at that frequency, whatever your signal frequency is, you've made the density of final states enormous, right, in a golden rule sense. So that's what ADMX does, but that's also what these ELPS experiments do. They put these Fabry-Perot cavities, and that drives the process by Q on one side and reconversion Q on the other side. It's a density of final, it's a golden rule argument. New star is a focusing argument, not a golden rule argument.
I have two questions. The first one is you had a diagram that shows the working principle of the instrument is a virtual photon interacting with an axion, but it's a real photon. What's the origin of virtual photon? Is it the magnetic field?
Yeah, the magnetic field. You have a cylindrical potential. And there's two ways to view it. One is you can view it as, depending on your druthers, process. I forget this, when you go to Fermilab and you send a photon beam to stuff, and a pion comes out off a fixed potential. I just forget what you call it. You can call it that. In other words, you can think of it literally as scattering off a cylindrical potential. The other thing that you can think of it is you can Fourier analyze spatially this cylindrical potential into modes. And then the trick they have to do is you have to turn a massive axion into a massless photon. It doesn't want to do that. But imagine that you pulled the right wave number out of that Fourier decomposition. Then it can go forward. That dispersion relation can go. It's matched. So one way to think about it is inverse Primakov production. And the other way to think about it is pulling out, when you Fourier analyze this cylindrical potential, the correct Fourier mode that allows this dispersion relation to go. That's two ways to do it. In any case, it's a zero energy photon that you're pulling out. It's static. And almost all, except for the recoil momentum, which is nothing, because it's in a big, it's the Earth, the recoil momentum. The axion energy becomes the
Energy of the photon.
energy of the photon.
My second question is, there's an indirect wave search that is looking for the photon decays from the wind. So are there any experiments that's doing for indirect search from axion decays to photons?
Well, this is an experiment that's sort of looking for axion decay photons. So the answer is, first of all, every WIMP experiment is an axion experiment. If you had a germanium counter, you'd be foolish not to look for axions. It's unlikely that you have the sensitivity, but every germanium counter and xenon detector has an axion search component. Secondly, there are experiments that look for the direct to photon decay. They're astrophysical experiments. Typically they are, you take a radio telescope dish, you point it at a nearby dwarf galaxy, the virial velocity of stuff in that dwarf is 10 kilometers per second. That's an exquisitely narrow line. So it's a wonderful thing to look for. You're looking for a very narrow line on junk, right? So you can see it. The problem there is you don't get enough rate until the mass is pretty high. As the mass gets up and up, the decay rate goes up. So even though the number density goes down, if I double the mass of the axion, the number density obviously drops. But there's an m to the 7th, right, in the decay. So you win big going to higher mass. So that begins to work at high mass. What people have run into, they started to do these experiments around 40 gigahertz or so. By the time you hit 100 gigahertz, you ran into the problem that there are many, 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 many uncatalogued molecular ones. For every candidate you have to do a spatial study of this dwarf galaxy. Namely, the dark matter isn't located right in the dwarf. There's an extended halo. So for every one of these candidates, you spend an enormous amount of time figuring out, does this candidate look like an axion in its kinematics? And of course, you want to make sure the rest mass is the same in all objects. So if you look at, Leo 3, and you look at some other dwarf galaxy, they should have the same dark matter in it. They're both well virialized, big mass to light ratio. They should both have axions. You better get the same rest mass. It better not be localized in anything like a molecular cloud. So the answer to your question is people have looked for direct, spontaneous decays of axion into photon and astrophysical halos. The problem is you need to go to somewhat high mass, and then you start running into this issue of how to deal with the large number of candidates from molecular ones. I don't have an answer to it, except it's very seductive, obviously, if you can figure a way forward.
Could you elaborate a little bit on optical implications of the existence of these axion guys? Does the universe have chirality if there exists in abundance and things like that? So we live in a sugar syrup or something like that.
God, I actually have no idea. I thought you were going to ask about optical decay.
No, so you said that, you said something about polarization rotation, that's what triggered this. Is universe a pseudo-scalar? So if you send something linearly polarized, it rotates, or?
It certainly ought to be the case. So there are
Yeah,
lots of
I would
sources
think so.
of polarized light in the universe.
You said by refringing, but it's even stranger, right? You need optical Lexus for that. One pseudo-scalar would be better than that.
I really don't have a good answer to you. I have to apologize. It's a question that I just don't quite have the answer to. So sorry.
All right. If there are no more questions, let's.
Yeah. So, you know that there are the catalog of the so-called cold dark matter. Hot.
Yeah. Yes.
I think Axions would belong to the so-called hot.
Well, you might think so, but perhaps a little more thought is involved. You make axions are produced cold. They're produced in a U1 phase transition.
Mm-hmm.
This is the same transition that, for instance, would give you Cooper pairs in a superconductor. The Cooper pairs are produced dead cold. They're all in the ground state. And the axion couplings are completely negligible. Therefore, they never thermalize. So even though they are exquisitely light, they're produced dead cold as a Bose condensate, and they never thermalize. So they remain cold dark matter. There's a very interesting question of whether that matters or not in structure formation. And there are two camps which don't agree with each other and don't seem to come to any agreement. There's a camp which says that, in fact, there are unique structures that can be formed with Bose dark matter that don't appear in, say, incoherent dark matter, WIMP dark matter. And there are others that say no, above some very short Jeans length, which is sort of 1 AU length, the structure is identical and classical field theory is perfectly adequate. And I can't claim that I have any insight into which direction to go in this. So,
Hey, let's thank the speaker one more time.